Hello, and welcome to GeneLab Chats. Today, we'll be interviewing Dr. Vitry from Staffordshire University in the United Kingdom and the International Space University. We know that human presence in space is limited by health risks associated with spaceflight conditions. While tissues such as muscle and liver are the most affected tissues during spaceflight, their relationship in response to space exposure have never been studied. In this reanalysis of two open science datasets, Dr. Vitry and colleagues explore the relationship of the response of both mouse and liver tissues during spaceflight. In this interview, Dr. Vitry will discuss this research and highlight how GeneLab's data systems and the AWGs enabled this work. Welcome, Dr. Vitry.
Thank you, Jennifer. I'm very happy to be here to respond to your question.
Let me start off by asking you, could you please let the audience know what were the most important findings in your study?
Yes, of course. Thank you for your question. So we know that spaceflight induces several biological changes in astronauts, among which are altered metabolism and muscle atrophy. The main finding of our study is that altered metabolism gene expression and muscle atrophy gene expression are two linked events in mice during spaceflight. The metabolism is a biological process that regulates energy resources in the body and within all cells. It regulates energy production, energy storage, and energy consumption according to the need and the environmental condition. Because the muscle, by its function, is a high energy demand organ, and because it represents up to 50% of total body mass, any alteration in the metabolism will strongly affect the muscle tissue. And conversely, any alteration in the muscle tissue will strongly affect the metabolism and the availability of energy for the other organ. During spaceflight, all cells of the body are exposed to space stressors such as space radiation, microgravity, or also altered day-night cycle. And all of them are known to promote DNA damage. And DNA damage repair is a high energy demand process. In our study, we found that high energy demand processes such as DNA damage repair, gene expression are downregulated, as well as the gene expression of energy intake and energy consumption, while in the liver, lipid metabolism gene expression specifically were altered. So these results suggest that during spaceflight, muscle cells enter in a power-saving mode where high energy demand processes such as DNA damage are downregulated and sparing resource gene expression are upregulated. This is kind of what we can observe during a starvation event. So thus, our finding suggests that spaceflight induces a starvation-like phenotype, and that this starvation-like phenotype could be at the origin of the muscle loss induced during spaceflight in astronauts. So our results are of importance for the planning of the future deep space and long duration mission, where astronauts will be exposed longer and longer to space stressor, but also for the understanding of metabolic disease here on Earth, such as liver dysfunction and diabetes, for example, and muscle atrophy. These two conditions, muscle atrophy and metabolic disease, are often seen together, like in space.
Thank you for that. And my second question is, how did the GeneLab database and AWGs help assist you in your work so you could achieve your goals?
So thank you for this question. I'm very happy that you asked that because I have a lot to say on that. So NASA GeneLab is a very powerful tool for space biology research and to anyone, anywhere in the world that would like to jump into this field. For myself, it helped me to pursue research activity during my year of master degree at the International Space University. It enabled me to lead my first ever project research in space biology and acquire new data analysis skills. And most of all, it enabled me to stay productive and competitive as a researcher, especially in the space sector. by publishing our results in a journal within a short time. So what we can say is that the main force of NASA GeneLab is that it gathered multiple kind of data from multiple species and across multiple missions using most recent and high-level technology. And this enabled to perform integrated data analysis, as we did in our study. We integrated data from the liver and data from the muscle. And a very interesting follow-up to the study will be to integrate as much as possible, as much data as possible, such as data from gene expression, but also protein and metabolites that are the endpoint of the gene expression. So this is what builds a phenotype, a particular phenotype. So doing that, we could get the whole picture of spaceflight-induced biological change. And the importance is that the more researchers can have access to this data and are aware of their existence, the more faster we can get this whole picture. And this is the open science mind of today's research, for which GeneLab is a pioneer. We used to say that space is for everyone, and NASA GeneLab truly promotes this spirit. I truly think that this is a spirit that will accelerate our return to the moon and enable us to go in further in the universe. Also, not only NASA GeneLab accounts for our interplanetary destiny, but it also enables to discover new insight and application for human health and disease. This is the case of our study from the GeneLab data, which enable us to provide new clue for better understanding metabolic disease such as diabetes and liver dysfunction, as well as aging-induced muscle loss.
Thank you, Dr. Vitry. This was inspirational. And to our audience out there, you can learn more about this work, how to join the analysis working groups, and access all the data sets analyzed in this work with the links provided in the description section below. Thank you and have a wonderful day.
Thank you, Jennifer. Bye.